Thank you very much, and I hope you can hear me well in the room. Is that correct?
Yes, we can hear you quite well.
Excellent. Thank you very much for the introduction and also for inviting me to join you at this meeting. Also, I'm sorry that I cannot be there in person, but I'm very happy to be able to join you over the internet. So indeed, I'm going to talk to you about the Envision mission, which is ESA's Venus orbiter mission in partnership with NASA, as we heard also from Tom Wagner this morning. And I'm making this presentation also on behalf of Adriana Ocampo, who was my co-chair for the Envision Science Study team until very recently, the study manager at ESA, and of course the whole science team for Envision. Next slide, please. So this is just an overview of our study science team and also other people working on the projects at NASA and ESA. It's not an exhaustive list, but just to give you some of the key names. And some people are also in the room here, like Candy and Walter, and we have some online like Emmanuel and Thomas Wiedemann as well. Next slide, please. So Envision is a ESA mission in the Solar System Explorers fleet. So it's in development. As you can see, the missions on the top of this slide. ESA also has had an earlier mission to Venus, as you know, the Venus Express mission between 2005 and 2014. And during your meeting, you've seen several results from that mission, which has been very important also, giving input to the Envision mission definition, where several of the instruments are actually forerunners to the instrumentation we will have, and where we will have some improvements to this instrumentation also for Envision. The planned launch date is in 2031, so that's still a while to go, but we're full phase now in the mission definition phase. Next slide, please. So this main science question for Envision, which is also which is a main question also from the previous missions, Veritas and Da Vinci that you have seen, is the big one. Why is Venus so different from Earth? And we had a very good presentation by Jim Heads on this this morning, showing the questions we have concerning Venus's history, whether Venus has always been as inhospitable, and whether Venus has been Earth-like, also potentially hosting oceans, and if they were there, how they disappeared. So Envision will address that by searching for ancient continental areas on Venus, which potentially preserve records of climate change, and also investigate how and when vast plains that cover most of the surface were formed. It will also look for and map impact craters, both recent ones and more older ones, to try and put in another piece of the puzzle for looking at the age of the surface. Concerning activity, Envision will also look for geological activity, which will reveal, as we heard before, more information about its plate tectonic engine. So Envision will look for distribution of geological activity on Venus, including volcanism and surface change, to help us better understand the geodynamic engine of Venus. And for the climate, as we heard also this morning, the big question is how the thick cloud layer of Venus is maintained unless there is active volcanism. And that has not been found. There are no clear evidence of active volcanism on Venus today, and Envision therefore is going to search for active volcanism in order to study also how that both impacts the surface and also the atmosphere, and to help study chemical and airline interactions with between the atmosphere and the surface, and also help studies of atmospheric transport mechanism, to look at the photochemical cycle of the atmosphere, etc. And in order to address this, we have 5 payloads on board and an experiment. Next slide, please. The first one being the VENSAR instruments provided by NASA. The instrument lead scientist is Scott Hensley at JPL. And this SAR is a heritage from the Earth observation NISAR SAR mission, and also, of course, of the Magellan mission at Venus in the 1990s. As mentioned by Sue, it's a 3.2 gigahertz S-band SAR, so different frequency than Veritas. And it will address the key science questions of Envision by doing imaging of pre-selected regions of interest at 30-meter resolution per pixel, so similar to Veritas, but also at finer resolution below 10 meters per pixel. And that will be essential for the reconstruction of the surface stratigraphy, as we heard earlier this morning, and also for revealing geological and chronological relations between different surface units. Comparison of different SAR images from VENSAR for the different cycles will be done, and also comparisons will be done with Magellan images in order to look for surface change, which is caused by, for instance, volcanism or tectonic activity and landscape forming processes. And that can be done hence on timescales from years to decades. We will have the same look geometry as Magellan. Surface topography will be addressed also through stereo imaging at regions of interest. There is a map here on the upper right showing some candidate regions of interest with interesting geographical areas with different geology inside. These are only examples of our regions of interest. And as we come closer to the mission launch, these will be refined and a final list will put together closer to the launch. And that's where also the science community can bring in some input here. We will have quasi-global topography coming from altimetry, and last but not least, we will have polarization imaging with two different polarizations, HV and HH, and also passive radiometry, which will give information about surface emissivity and roughness. Next slide, please. So the next instrument is a subsurface radar sounder, the first one that will orbit Venus. And it has heritage from JUICE RIME and also from MEX Mars's and Emerald Shard. Instrument lead scientist is Lorenzo Brunzone at University of Trento. And this one is a fixed dipole antenna at 9 megahertz, which will be providing information on surface roughness, composition and permittivity, and also observe impact craters and their infillings, buried craters, tessera, plains and lava flows on their edges. So that will be an important instrument to add to the observations on the surface by the SAR instrument. It will have a penetration depth down to 1 kilometer, depending on the rock types and the type of layering that is there at about 20-meter vertical resolution. We then have a spectrometry suite with different spectral imagers. The first one being VenSpec M, which is the same type of instrument that will also be on Veritas. It's a native pointing push broom spectrometer looking at 14 near-infrared transparency windows, and that will be used to do surface mineralogy. So looking at this, the signals in the different bands in order to classify the rock types on the surface, as was shown by Sue before. It will also be used to monitor volcanic activity through surface emissivity observations to an accuracy of better than 4%. And the mapping of the near surface water and also optical cloud variability will be used primarily to do atmospheric corrections of the surface observations of surface emissivity. We can also give the bigger contents of water vapor and cloud dynamics. Next one, please. Cloud variability. The two other VenSpec instruments are VenSpec H and VenSpec U. VenSpec H being a high resolution spectrometer. It's led by Anne-Carine van Dale at BISA in Belgium, and it has an heritage from Vexois and Nomad, but this one will have much higher spectral resolution and also look in near infrared spectral windows, so it will be able to map both the troposphere and the mesosphere with different trace gases such as SO2, H2O, HDO, and also CO and OCS. And this will be very important to characterize volcanic plumes. So it will look all the way down to the lowest 15 kilometers of the atmosphere, and also to look at sources for other of trace gases, and to provide information about the chemical composition and cycling. The Venspec H is a UV spectrometer, nadir pointing as well, which will cover 190 nanometers to 380. So it will be used to map SO2 above the cloud deck. And that is to support the research for volcanic activity, but very much so also to understand the sulfur cycle. It will map the upper cloud and aerosol properties, and in particular, it will investigate also the variability of the unknown UV absorber. The next slide, please. So last but not least, the radio science experiment is using the radio signal to Earth in order to do gravity and radio occultation measurements at the accuracies and altitudes, as you can see at the bottom of this slide. So it will determine the Venus gravity field with an accuracy of 0.2 millimeter per square second at the 270 kilometer resolution, or even finer for some modes, and also be able to determine the K2 love number at an accuracy of 0.01, which will be used to constrain the inner structure of the planet. The radio occultation will also for the first time be able to measure sulfuric acid liquid droplets between 45 and 55 kilometers. And also sulfuric acid vapor from 35 to 55 kilometers. And it will also provide temperature and pressure and density profiles. And it will do the radio occultation, as Thomas Wiedemann said in the chat yesterday, 2 times per 24 hours, about 50% of each cycle. So that will be much more abundant radio occultation measurements than we have had seen from earlier missions. Next slide, please. So the novelty of Envision will be really to look at the Venus system from the interior all the way up to the mesosphere. And it will do that on regional and in some cases also on global scale. So that's very complementary to the Veritas mission and the Da Vinci mission, which will look globally, will focus on the surface, or will have these very high resolution, very precise atmospheric chemistry measurements, but more locally over the alpha region plane. So the mission will clearly further European, but also international planetary and exoplanet science community by providing a large amount of data, which we will provide for free public access 6 months after data take for the raw data from the mission. And at a little bit longer time scale, also derived data products will be made available. It's very complementary, these missions, and also they're complementary to past missions. So we have these, as Sue and Jim was also mentioning, the need for multi-temporal radar imaging, which will give you information about surface change detection. And by putting together the data sets from Magellan, Veritas, and Envision, you can really look at change detection by comparing data over several decades. We will see how now how the phasing will between Veritas and Envision, if they fly together or differently. And as you were saying, if they are flying in a row, change detection can be done by comparing these 2 different data sets in time. Also, the atmospheric composition is important to observe over time to fully understand it. And there we can put together the data from all of the previous missions and the upcoming missions here, looking at different scales. And also for the gravity observations, as Sue was also mentioning, it's important to have these together. Next slide, please. So coming to the mission timeline, we're now in phase B1, which is where the preliminary design is done, and we'll have the mission adoption in February next year. And we will start to have the final design of the instruments and the spacecraft, and we'll start to build the hardware. The launch is around 2031, or actually it's scheduled for November 2031, but that will be confirmed at the mission adoption, also together with NASA. We'll have a high Earth orbit launch with a direct escape and a cruise time of about 17 months, depending a bit on the performance of the launcher, which is currently to be provided, and an aerobraking phase of about 70 months as well. An in-orbit commissioning of the instrument and the start of the data take in autumn 34 and the end of the science operation in 38. Next slide, please, which is coming to my conclusions. Perfect. Indeed. So Envision will indeed give a holistic view and will be very of Venus and be very complementary to the other missions. It would also help to give information for exoplanet studies to understand the differences between Earth and Venus in more detail. Aerobraking science will also be used to obtain information above in the ionosphere, so above 130 kilometers. And it will be very complementary to the other missions. The VESCOR group was mentioned by Tom Wagner this morning, and that is hopefully going to start up soon and will bring the Venus science community together to discuss these three missions together. And we will also have topical workshops coming up and form working groups as we come into the next phase, where we hope to have a larger part of the science community to join us. We will also have a workshop from the 9th to the 11th of May. Next slide, please, in Berlin. So we all invite you to come there, submit your abstract before the 1st of March, and meet us there to discuss Envision and also synergies between the missions. So welcome to join that, and thank you for your attention.